Okay, so we'll go ABC here. I am going to use elimination, and what variable should I eliminate? Y. That seems to be the easiest one. You are correct. So I'm going to do over here, give me B and C will work, so let's do B plus C. So if I do B plus C, I've got X and X make 2X, positive Y and negative Y cancel out. Negative Z and positive 2Z, positive 1, 0, just Z. Negative 9 and 7, negative 2. So what equation haven't I used yet? A, I'm going to add that to B, because negative Y and positive Y will cancel out there too. So I have to use the equation I haven't used yet, and I have to use repeat one of the other ones yet, or a multiple of one of the other ones, depending on how it works out. So 2X plus X, 3X. Negative Y plus Y goes bye-bye. Negative Z plus negative Z, negative 2Z, and negative 8 plus negative 9, it's negative 17. So this right here is now a system, 2 equations, 2 variables. That was easy because the Y's automatically canceled. I didn't have to multiply any of them. Most times I'm going to have to multiply at least one of the equations to make everything cancel out. So now what I'm going to do here is I'm going to multiply this top one by 2. So that's going to give me what? Perfect. 2 times 2x is 4x. 2 times z is 2z. Then equals 2 times negative 2 is negative 4. Because I am now going to combine those 2 equations. 3x and 4x, 7x. Negative 2z and positive 2z goes away. Negative 17 and negative 4. There's 1. And then x equals negative 3. Now we have to find one of the other variables. Now we go back through the order. We go backwards. The last set of equations we used were these, so I got to use my x equals negative 3 in there. I'm going to use the top one, 2x plus z equals negative 2. So yes, this is negative 6 plus z equals negative 2. We finished that off by, there you go, adding 6. Z equals 4. Now I go back to one of the originals. Doesn't matter which, I'm going to take this one because y is positive. So I've got x is negative 3 plus y minus z is 4 equals negative 9. Negative 3 and negative 4 make negative 7 plus y equals negative 9. And then I add 7. Y equals negative 2. So my solution is negative 3, negative 2, positive 4. More fun than a barrel of rabid monkeys? So what we're going to talk about today, briefly, is matrices. What a matrix is nothing more than an organized set of numbers. Might look something like this. That is the matrix. The brackets around it, those square brackets tell us it's a matrix. A matrix has dimensions. These are called the rows. These, of course, are called columns. And the dimensions of a matrix is just the row and the column. So this would be considered a 2 by 3 matrix. It's not multiplication. It's not a 6. It's 2 by 3 is what that stands for. So it's saying 2 rows, 3 columns. Well, what we're going to be looking at, we're going to be focusing on a special type of matrix called a square matrix. And what's special about a square matrix is the number of rows equals the number of columns. In other words, it's square. And the reason we're going to focus on that is because on a square matrix, there's something you can do called a determinant. And a determinant takes into account the values of every number in the matrix. And it's weird that you wouldn't think you could summarize the whole matrix with a single number, but you kind of can. For example, if I have the matrix 3, 5, 2, 7, and I want to do its determinant. Well, determinants use what's called diagonal products. If the diagonal goes down, it's a positive. If the diagonal goes up, it's a negative. Now, that doesn't mean that the value of the numbers can't change that. So in this matrix, in a 2 by 2 matrix, it's very simple. There is one down diagonal, that'd be 3 times 7, right? Which is 21. So that's your down diagonal product. And there's one up diagonal. 2 times 5 would make 10. Because when we go to combine them, the 21 stays positive. We subtract the up, the 10. So 11 is the determinant of that matrix. Now, you wouldn't think 11 could totally summarize that matrix, and it doesn't. There are a lot of matrices we could create that will have a determinant of 11. But there's a special characteristic about matrices with a determinant of 11 that is consistent between all of them. Now, rather than saying I want you to do the determinant, there's a symbol slightly different from the square brackets. It's just using straight brackets like this. That is saying those straight brackets like that are saying find the determinant. So when I have those straight brackets, I can jump right in. What am I going to do first? 2 times 1 is 2. Negative 3 times 7 is negative 21. And then when I combine them, it's 2 minus a negative 21. That's a 23 determinant. What do you think? We'll get there. This one might take a day or two to get to. The 2 by 2 matrix is pretty simple. In a 3 by 3 matrix, obviously, I cannot do just one down diagonal and one up diagonal because we miss almost half the numbers if we do that, don't we? So what we do is we do several diagonals in each direction. So going down, I have 5 times 5 times 3, which is 75. Then I start from every entry in the top row, I start a down diagonal. I do 4 times 1. Well, what do I do down here? You ever play the game Asteroids? You ramp off the side of the screen and you appear on the other side magically like that. 4 times 1 times 2. Let me show you an easier way to think of that. I'm going to take the first column and rewrite it. And the second column and rewrite it. So this is just 4 times 1 times 2, which is 8. 2 times negative 3 times 7, negative 42, right? If I add all of those up, I have 83 minus 42, that's a 41. That's my down diagonal total. Any questions on how I got the 41? So then I do up. 2 times 5 times 2 is 20. 7 times 1 times 5, 35. 3 times negative 3 times 4, negative 36, right? That adds up to 19. So my determinant is 41 minus 19. 22 is the determinant of that. Does that make sense? What's that? Why would you do that? Because if you can calculate the determinant of the matrix, you can calculate the solution to a system of equations. And it's going to take us a couple days to get there. Yeah. Yeah. This is the way a computer or a calculator actually handles numbers, and this is how a computer or a calculator would actually calculate the solution to a system of equations. Let's play with this one. Now, again, the first thing I'm going to want to do is, yes, I'm going to rewrite those first 2 columns. Now I'm going to go down. Negative 2, 0, negative 4, of course, there's a 0 in there, so that's a 0. Plus 3, 2, 3 is, careful, 18. 5, 1, 5, 25, that adds up to 43. Now, first of all, everybody see where I got the 0, 18, and 25? I'm just multiplying each diagonal. Negative 2 times 0 is 0, 0 times negative 4 is 0. 3 times 2 is 6, 6 times 3 is 18. 5 times 1 is 5, 5 times 5 is 25. Now I have to go up the diagonals as well. 3 times 0 times 5 is 0. 5 times 2 is 10, times negative 2 is negative 20. Negative 4 times 1 is negative 4, times 3, negative 12. That adds up to a negative 32. So our down is 43 minus our up of negative 32. This is the determinant of 75. We'll get to those. Try that one in your notes. So we do, of course, rewrite the first couple of columns at the end. Then we'll multiply. 2 times 1 is 2, times negative 1 is negative 2. Negative 3 times 4 is negative 12, times 2 is negative 24. 0 times 5 is 0, so that's going to be 0 no matter what. So that gives us a negative 26 on the down. Going up, 2 times 1 times 0 is, of course, 0. 3 times 4 is 12, times 2 is 24. Negative 1 times 5 is negative 5, times negative 3, positive 15 gives us 0, 24, and 15 make 39 on the up. So we have a negative 26 minus a positive 39, which is a negative 65. How many of you had negative 65? Cool. Questions on where that negative 65 came from? It's always the down minus the up. It's the down minus the up. There's something called expansion, which we will talk more about tomorrow. We've got to have something to play with tomorrow, right? What an expansion is I'm going to pick any number, any entry. You guys pick an entry in that matrix. Somebody pick one, yell it out. 1? Okay, the 1. Every entry in the matrix has two things we consider of it. One is called a cofactor. A cofactor is either just the entry or negative 1 times the entry. How do we know? It's based off of position. If it's in an even position, the cofactor is just the entry. If it's in an odd position, the cofactor is negative 1 times the entry. What do I mean by position? What row is that in? Row 2. What column? 3. What is 2 plus 3? 5. That is odd. So the cofactor here is exactly right. It's negative 1 times the entry is 1. So negative 1 is its cofactor. Every entry also has a minor. The minor is a smaller matrix. It is found by removing a row and a column. What does that mean? Well, the 1 is in row 2, it's in column 3. So I remove row 2 and column 3. And I get a matrix 2, 7, 3, 5. That is the minor. We will talk more about cofactors and minors tomorrow. And that would be 10 minus 21, so negative 11 would be the determinant of that minor. So the expansion value of this of 1 in this matrix is its cofactor times the determinant of its matrix. So that's 10 minus 21 is a negative 11. So negative 1 times negative 11 is a positive 11 would be the expansion value. Well, you have that quiz to finish up, and I have a happy little worksheet I'm going to give to you.